Good morning, everybody. It is about to be 8 o'clock sharp. We've got a lot on the docket for today. Exam 2 review and Chapter 5. So I posted the Exam 2 review packet late last night. It's fairly short, and this exam that's coming up is on Chapters 3 and 4. Chapter 3 is probably the easiest chapter that you'll have this semester. And Chapter 4 is probably a little bit more on the abstract side. So I've got some Exam 2 review questions, and we'll do some more kind of review of Chapter 4 as we cover Chapter 5. So I'd focus a little more on Chapter 3 questions for the exam review. Your exam is going to be multiple choice, and it's pretty much all concepts, very little math. So if you think of any questions that you have about the exam, you can let me know. You can put them in the chat, and I will get to them as I am able. Before we start Exam 2 review, does anyone have any questions? Oh, one more thing. Mastering chemistry. I know Pearson was struggle bus this weekend. I had a bunch of people email me, send me course messages about mastering. Don't worry about it. I got you. So you have an extension. You can finish it up, and you have until the end of Wednesday. But you really want to finish up chapters 3 and 4 because you have chapter 5 due on Sunday, and you have an exam on those chapters. So you really don't want to let it drag on. And in the future, try to get it done before the day that it's due. I know sometimes that's not possible, but even if you work on it for 30 minutes, and you work on it for like 4 days, 30 minutes at a time or so, even that is better than trying to cram it all in on Sunday. So if you completed mastering, look at your grades on Blackboard and see if the grade that you got is what you think it should be. Make sure that the system updated properly. If not, you may have to go back and redo some things if Pearson was really on the struggle bus. I'll probably make that announcement again about mastering about halfway through, just to make sure I catch everybody. So if you have any questions about Exam 2, about mastering, or anything kind of logistical, this is the good time to ask. So let me know in the chat. And just let me know how you're doing, how you're feeling this morning. Hopefully everybody's all right, well rested, feeling healthy. Because it's flu season. We still got COVID. All sorts of stuff. Weather don't know what it want to do. My allergies were acting up. Because it said 70 degrees. Must be pollen. So I had some struggles over the weekend. But let me know how y'all are doing. If we're ready to start exam review, or if you have some questions, let me know in the chat. All right. Well, let's go ahead and get started. Exam 2 is going to be multiple choice. So I've got multiple choice questions here just to give you a selection of what it'll be like. Here's our first question, and I'll give you a couple of minutes to work on this. Hopefully you have your periodic table. So make sure you have that periodic table that I posted. I will give you can print that off for the exam. So that's really the only thing that you're going to be able to have for exam 2. There is no equation sheet because ain't no equations. So periodic table is what you get. I'll give you 2 minutes to read over the question, and you can put your answer in the chat. Alrighty, so I see we have a couple of answers coming in, and I'll help you shake the cobwebs off. This question is asking how many neutrons are in the nucleus of an atom of cobalt-60. Remember that cobalt-60, that is an isotope of cobalt. That means it has 60 for its mass number. Which is equal to the protons plus the neutrons. The protons you get from the atomic number. Which is on the periodic table. So if you look at the periodic table, the atomic number is 27 for cobalt. So you subtract 27 from both sides. And you should get B. Which those of you who answered already in the chat, that's what you got, so good job. Any questions on this, or can we move on to the next exam review question? And let's go on to the next one. Which of the following properties of gasoline is a chemical property? I'll give you a minute to read it over, and you can put your answer in the chat. Okay, so it seems like most everybody said E, and I would agree with that. None of the above. A, B, and C. What would we classify those as? Colorless liquid, density, boiling point? Is it a chemical change, physical property, physical change? Yeah, all of these are physical properties. Good. Here's a math one. This one is one of those weighted average questions. So I'll give you more like 3 minutes or so to read through and work it out. And then I will hop on and start solving it for you. All right. So I'm going to get started on this one. We've got element X, 2 natural isotopes. I'm going to start by making the chart. So there's all of the categories that I need. We've only got 2 isotopes. I'll use my highlighter here to show where we're getting the information. Oops. So the highlighting is to show you where I got the information from in the problem and how I put it into the table. Everything else that I fill in is going to be something that we've figured out. Notice that there is no percent abundance for X65. But you can still figure it out because the total abundance should add up to 100%. So you do 100% minus 69.17%. And that'll give you 30.83. That is the key to solving this problem. Without doing that step, you can't solve it. Now we can write our percent abundance as a decimal. And the way to convert is to divide by 100. Then you set up the equation. If you didn't get an answer, try to put this into your calculator and see what you get. And you can put your answer in the chat. So you can choose, A, B, C, D, E, and put it in the chat. Oh, shoot. So once you have that in your calculator, make your choice about what your answer is. Because I see we have one answer up. I'd like to see a few more, see what you guys are thinking. At least be able to put it into your calculator from here. So with sig figs, it should be A. So make sure you know how to do these types of problems. Questions about this one, or are we ready to move on? Okay. So in this one, we've got 2 questions. And this first one about the limestone, a little bit of a throwback to chapter 3 because we haven't talked about it in a while. So I'll let you do both of these questions. I'll give you 2 to 3 minutes, and then we'll go over them. So let's go over these 2 questions. The top one, you might be scratching your head like, what? Where did this come from? This is at the end of chapter 3. We've got limestone that decomposes by heat to give 8.51 grams of solid calcium oxide and 1.60 grams of carbon dioxide gas. What was the mass of the limestone? Now, I told you exam 2 is going to be multiple choice. These 2 are not multiple choice questions, but on the exam it would be. This is a conservation of mass question. Remember that with a chemical reaction, you're not going to just have some reactant that just disappears. So the same amount of reactant that you start with, you're going to have that same amount of products. The other way to say that is the mass. So the mass of the reactants is equal to the mass of the products. The reactants, well, there's only one in this case. That's the limestone. And the mass of that is going to be equal to the mass of the 2 products. So that's the calcium oxide and the carbon dioxide gas. We're given the masses for these. So all you have to do is add them up. So your answer there is 10.11 grams. Questions about that one? You just have to remember that we did conservation of mass at the end of chapter 3. I'll take it that there are no questions. If there are, let me know. But I'll move on to the next one. How many carbon atoms are in triolene, which is a vegetable oil? We've got that. We've got this. And with these parentheses, we've got to worry about that 3. So the number of carbon atoms that we have is going to be 3, which comes from here, plus 3 times 17. Because we have to take the 3 that is on the outside of the parentheses and multiply by the number of carbons that we have on the inside. And I would agree with you all that the number of carbons is 57. Is that right? Any questions? Oh, I didn't circle this one. I'm sorry. Okay. All right. That's the exam 2 review. We focused mainly on chapter 3. We're going to talk about electron configurations in chapter 5. So we'll get some review there on that. You'll have to review kind of the history of the models of the atom for chapter 4. But I think that that's pretty straightforward. There's no tricks, there's no real concepts until you start getting to the energy levels. So I have office hours today from 11:30 to 1. If you have questions and you can stop on through, go ahead. The exam 2 review is posted with the answer key. And like I said, this is going to be a multiple choice exam. I'll also take the opportunity to catch the rest of y'all who logged on a little bit later. If you had questions about mastering chemistry, struggle over the weekend, don't worry, I got you. So I sent out an announcement late last night, but I'll reiterate in class. You have an extension, get it done by the end of tomorrow. So I've, moved the due dates. So if you did work on it and you don't see the update in your grade, it could be because it wasn't recorded in the system. So Blackboard may have been doing some site maintenance or something like that, or they just had an issue. Outages happen. So check and make sure that the work you think you did over the weekend was actually recorded. And if not, you may have to go back and redo some things. Okay. So we'll start with chapter 5. Again, this one kind of starts with a little bit of a history lesson. So I'm going to lean on you guys to watch the video that's posted to YouTube for that. What I want to focus on is some of the concepts and doing some practice problems together, just to give you a little bit of practice with some feedback. So the first part of the lecture that's on YouTube already really talks about the history of the periodic table, and then it goes into details about how the periodic table is organized. So again, not going to go through all of that. That's just kind of a history lesson. You need to know it, but I'm not going to spend time going over it. It'd just be me reading slides. Nobody wants that, especially me. My throat is sad, all right? I do want to take a little bit of time to talk about the organization of the periodic table, just to let you know the kind of information you need to know for the exam. Not exam 2, but exam 3, because we are ever pressing forward. So this slide is just to kind of give you an idea of what you need to know. You'll need to know how the periodic table is arranged. We've got groups and we've got periods. Groups are the columns. Periods are the rows. So I write it like that because it reminds me a group is a vertical column, a period is a row. Each of these periods corresponds to an energy level. So if you are in the second row, that's the principal energy level 2, N equals 2. If you're in the fifth row, it's N equals 5. You'll also notice that there are numbers above each column. Well, each group has a number designated to it. There's 2 different numbering systems. The one that I prefer is the American convention that has a Roman numeral followed by an A or a B. That's because it gives you more information than just 1 through 18. Okay. The A's tell you representative elements. The B's tell you that you have transition elements. Again, all of this information is in the YouTube video and in the lecture notes for that. So I'm not going to write down a whole bunch of stuff and, just giving you the overview of the types of things you need to know. You'll need to know so we talked about transition elements, representative elements, the lanthanides and actinides down here. And notice some of these groups have common names like alkali metals or alkaline earth metals. You'll need to know which groups those are and what their common names are. I spell out exactly what you need to know in the video. But you pretty much need to be able to replicate this slide, knowing where the transition elements are, representative elements, lanthanides, actinides, common names, that kind of thing. Let me know if you're with me in terms of understanding what it is you need to know from Chapter 5 with this periodic table. Let me know if you're good. Give me that thumbs up if you're ready. Okay. We're going to move on to periodic trends. If you have a periodic table that you can draw on, I'd recommend doing that for these trends and have it be separate from the Chapter 4 one with all of the energy levels and sublevels and stuff. If you don't have a periodic table to draw on, you can always print one out, but I recommend that you have one with the periodic trends. The first trend we're going to cover is atomic radius. That's literally the size of the atom. So if you have an atom with a nucleus here, what this circle represents is the outermost electrons. And that's going to be the furthest distance away from the nucleus. That radius decreases as you go up a group and as you go from left to right across a period. So if you have your periodic table, you'll want to draw an arrow up and an arrow from the left to the right, and maybe you want to color code it or something like that, and put atomic radius decreases. So this is an example. We've got some of the elements represented here. Notice that the transition elements, there's a lot of exceptions there. So for this atomic radius trend, we're really only talking about the representative elements. Not the transition elements. If we think about this, it kind of makes sense. At the very top, we've got our n equals 1. At the bottom of this diagram, we've got n equals 5. And in chapter 4, we said that the higher the energy level, the n, the farther away those electrons are going to be. That means that the radius of the atom has to increase when the energy increases. As long as you know increase in n means an increase in size, then you'll be good to go. Questions about atomic radius? Okay. Now, one more thing to note, just for your own kind of understanding. That's within a group. If you're going from left to right, you're within the same energy level. So you're adding electrons to the same space. So the best one to do would be, let's talk about these elements here. Okay. These are all in the 2p sublevel. You're adding electrons to that same sublevel. That sublevel is not getting bigger. The energy level isn't getting bigger as you're going from boron all the way across to fluorine. We're just adding electrons. And adding electrons means that you're going to increase the attraction between the electrons and the nucleus. That leads to the atomic radius actually getting smaller because the electrons are drawn in a little bit more to that nucleus. So that's just an explanation of the why. If you don't care about the why, that's okay. Just know the trend. Everybody here ain't trying to be a chemist or any type of scientist, and I understand that. So just get the information you need. But if you're interested in a little bit of the why, there you go. The next trend you'll want to have on your periodic table is a metallic character. And what that indicates is how easily an element gives up an electron from its outermost energy level. So what we're talking about is this point right here. This is what metallic character is. It has the same trend as atomic radius. As you go up a group and left to right across a period, metallic character decreases. So if you know atomic radius, you also know metallic character. What we can also talk about with periodic trends is physical and chemical properties. When elements are in the same group, they have similar physical and chemical properties. The elements that are listed in this table, which I used it in the video, so if you're like, this looks familiar, it's the same one. I just blocked out the very top row so that we can talk about it. We've got elements lithium, sodium, potassium, rubidium, cesium. These are all in group 1A on the periodic table. And if you have one, you can look at it and you'll see all of these elements are in group 1A. Also in this table, we've got a bunch of different physical properties: radius, density, melting point, and mass. Cesium is the heaviest. This is towards the bottom of the periodic table. Lithium is up there at the top. We can look at the trend going from the bottom to the top to make some predictions about what we think lithium will be. Atomic radius, we just went over that trend, right? That as you go from the bottom of a group up to the top, the atomic radius decreases. But if for some reason you didn't know that and you just had this table, you could look at it and make the same conclusion. We're starting with an atomic radius for cesium, which is down at the bottom, at 266 picometers. As we go up, the radius decreases. So if you had to guess what the radius is for lithium, at the very least, you could say that it's going to be less than 186 picometers. Since that seems to be the trend, it's going to be smaller than what came before it. With the density, we can do a similar thing. We're starting at 1.87 at the bottom with cesium. And as you go up this group, in general, you see that the density decreases. It's common to see little, inconsistencies like sodium and potassium. Sodium is a little bit more dense than potassium, but it's not a big deal. But chances are the density of lithium is going to be definitely less than 0.97. It might be a little less than 0.86, but it's certainly going to be less than 1. Does this concept make sense, where you can look at other information about elements in a group and make predictions? Because that's all we're doing, looking to see what the trend is. So let me know if this makes sense to you. Let me just hit you with a question and see how we're doing. Melting point. I'm going to give you some options, and I want you to tell me which one seems like it could be a melting point for lithium. Which one of these choices that I just wrote could be a melting point for lithium based on what you see in this column? Yeah. It's definitely going to be more than the 97.8. So we get the concept. Let's move on and do some practice problems. Predict the density of barium given that the density of calcium is 1.4 grams per centimeter cubed and strontium has a density of 2.63 grams per centimeter cubed. And I gave you the column in the periodic table. So this is the group that barium, calcium, and strontium are all in. I'll give you a minute. Try to figure it out and put your answer in the chat. Let's talk about it. We're trying to predict the density of barium, which is here. We're given information for strontium and for calcium. The trend seems to be that as we go down, density increases. So we know off rip it's got to be something that's bigger than 2.63. So we can throw out A, B, and C. We know it can't be any of those. We're down to either D or E. We can look at the numbers. The difference between 1.54 and 2.63 is a little bit over 1. So the difference between strontium and barium will probably be in that same ballpark. A little bit more than 1 gram per centimeter cubed. So your answer should be D. E would be too much of a difference. And if you do the math, if you're a math type person, you can subtract 2.63 grams per centimeter cubed. You can subtract 1.54 from the 2.63. And you get 1.09. You take that 1.09 and you add it to, this is the strontium density. And you'll get 3.72 for barium. So the couple of you that did respond in the chat, you got it right. So hopefully y'all who did not, hopefully you understand the concept. And either you can just do mental math or you can do it out and get an actual number if the math makes more sense to you than the concept. So how do we feel about that one? Are we good to move on, or do we need another practice? Excellent. Then let's talk about chemical properties. We can also predict chemical properties for elements in the same group. If you know the chemical formula for one element mixed with another, then you can make the same guess as to what the formula is going to be for similar elements doing the same chemistry. So the formula for the chloride of calcium is CaCl2. That means that you've got 1 calcium atom and 2 chlorine atoms. What is the formula for the chloride of magnesium? You'll need your periodic table here. If you have one, tell me if magnesium is in the same group as calcium. Are they in the same group? Remember that a group is the vertical column and the period is the row. So magnesium and calcium are in the same group. They're in the same column. Magnesium comes above, but they're still in the same group. That means that magnesium is going to have a similar formula. And if we go back one slide, that's magnesium right there, right above calcium. I did that on purpose. Sometimes I'm good at this, y'all. So that's magnesium right there. It's in the same group. If calcium is in complex with chlorine, and there's 2 chlorine atoms, magnesium is in the same group. So our guess for the formula of the chloride of magnesium is going to be MgCl2, just like the calcium. So when you see a question like this on exam 3, don't freak out. It's really that simple. Just replace, as long as they're in the same group, then you write it the same way. So I want you guys to do a practice. The formula for the oxide of sodium is Na2O. What is the formula for the oxide of potassium? You can put your answer in the chat. Don't worry about the formatting with the subscript. It's all right. As long as the numbers are there and they're right, it's all good. So take a second. I'll give you a minute. Give folks a chance to drink it in and put up an answer. And if you think that's the answer, if you agree, you can put same. Or you can do the little caret, saying, yeah, that. Potassium and sodium are in the same group. So if it's Na2O, then our formula is going to be K2O. It is that simple. So make sure that those 2 things are in the same group. If they're not, then you can't answer the question. We good on predicting chemical properties? Now we're getting into the good stuff. I wanted to make sure we had plenty of time to go over electron configurations because we're going to build on what we did from chapter 4. So the first thing we're going to do is refresh on how to write a full electron configuration. Then I'll introduce the noble gas electron configuration. I found a video, I want to say it was last semester, is a really good video on how to write these configurations. Somebody remind me, because I want to post a link to that video in chapter 5. So in the folder for chapter 5, remind me that I want to post a link to a YouTube video. It ain't mine. I found it. I thought it was really good to help you with writing electron configurations. So if somebody want to send me a course message or something, or remind me at the end of class, Dr. Hefner, don't forget about that video for that thing. Very much appreciated. So here we go. We have to write an electron configuration for boron. Before we start writing, I'm going to label this periodic table. This is a partial periodic table, obviously, but I want to try to refresh your memory about some of the things we said for the periodic table. Everything in black is the s block. We're filling an s orbital within that s sublevel. Everything in purple is the p block. We're filling the p orbitals within the p sublevel. In the middle here with these transition elements, that's the d block. We're filling the d orbitals within the d sublevel. These are the sublevels, 1s, 2s, 3s, 4s. So that speaks to the energy level. The main energy level would be 1, 2, 3, 4. The S tells you the sublevel. It's the S sublevel. The S sublevel only has one orbital. For the P's, we've got 3 orbitals. For the D's, there are 5 orbitals. Each orbital holds a maximum of 2 electrons. So for example, in the 1s, you've got hydrogen, which has 1 electron. So that means the 1s sublevel has 1 orbital, and that orbital has 1 electron. Now let's go through and write the electron configuration for boron. You always start by filling the lowest energy sublevels first, and you continue to fill each sublevel until you get to the number of electrons that your element has. We're going for boron, which has 5 electrons. Start with the 1s. The 1s can hold 2 electrons. 1, 2. We're not at boron yet, so we need to keep going. We've got 2 electrons so far. We drop down to the second energy level. So this is the second row. We're now in 2s. How many electrons can the 2s sublevel hold? Yes, it can hold 2 electrons. Now we've got 4 electrons. If we stopped there, we would have the electron configuration for beryllium. But that's not what we're looking for. We're looking for boron. So we have to go across to the p block. How many electrons do I need to put in the 2p to complete my electron configuration? 1. That is the full configuration. For boron. But what if we didn't have to write all that? What if we could use noble gas configurations to show, okay, we've got all of these rows filled, and to add on to it, we've got these electrons in this particular period. That would be pretty easy. I'm going to switch colors here to red. For the noble gas configuration, you want to find your element. We have boron. That's in n equals 2, right? It's the second row. That's the second period on the periodic table. You want to use the noble gas in the period above your element. This last column here, these are the noble gases, which I abbreviate Ng. If we need to write the noble gas in the period that comes before boron, what noble gas is that? You can put its element symbol in the chat. What is the noble gas in the period before boron? We're looking for something from this row here. Or from this group here. Because it's this last group that are noble gases. Yeah, it's got to be helium. We were looking at boron. It's in n equals 2. We have to go up to n equals 1 and go over to, this is group 8A. Group 8A, that's the noble gases. You find the noble gas for n equals 1. That's helium. If we were to write the electron configuration for helium, it would be 1s2 because it's got the s completely filled. And what you'll notice with the noble gases is that all of their available orbitals are full. There's no more room for electrons. Once you write that down, then we're here. That's our equivalent of writing 1s2. Doesn't save us a whole lot for this one, but in next ones it will. After that, you have to write all of the electrons that are being added to the sublevels to get from helium down to boron. That's everything in the n equals 2. So for the noble gas configuration, You find the noble gas in the period above the element you're interested in. We were interested in boron. That's an n equals 2. So we go up to n equals 1, and we find the noble gas in group 8A. That is our noble gas core. Then you write all of the electrons outside of that core. So everything that's added in n equals 2, we have to write. The 2s2 and the 2p1. Let's do another example together and make sure that that hits right. So is everybody ready for me? Can I move on from this slide? If you're taking notes as I'm going along, let me know if you have everything down that you need. If you're ready for me to move on, let me know. Okay. So let's do the electron configuration for aluminum. We're going to do the full configuration first, then we'll do the noble gas, just for practice. Then for the last one, we'll just do the noble gas configuration. So I'm not labeling the blocks, but I will write out the sublevels for you. Help me write this configuration for aluminum. Aluminum is here. It's got 13 electrons. I'm going to fill the 1s. How many electrons am I putting in it? I'm going to put 2. What's the next sublevel that I have to fill? I've got to fill that 2s. And it's going to have another 2 electrons. Still a ways away. What is the next sublevel that I fill? I hop across to the 2p and I fill that. What's next? And what's next? So Malachi just bodied that. Thank you. If that was a little too fast, I'll give you a second to drink it in. That is the full electron configuration for aluminum. We started with the 1s because it is always the lowest energy, and we kept filling until we got to 13 electrons. Remember that you don't have to completely fill all of the sublevels. You're just filling until you reach your element. So that's a common mistake that I see, where you feel like you have to fill the entire P just because you're in the 3p. No, aluminum only has 1 electron in the 3p, and that's perfectly fine. Now let's do the noble gas configuration. We need to choose the noble gas core. Aluminum is in the N equals 3. What period do I need to go to find the noble gas to use for the noble gas core? I have to find N equals 2. Once I do that, I find the noble gas in N equals 2. What is that noble gas? It's neon. So my core is going to be neon. What that means is that everything in the 1s and the 2s are filled. So what I'm putting in these red brackets, that's neon. If I were to write the full configuration for neon, that's what it would be. These brackets with neon, that's taking the place of 3 different things that you would have normally had to write. Now let's finish it out. Aluminum has more than just 10 electrons. It's got 13. So we need to go from where neon is to where aluminum is. How do I finish out this configuration? What do I need to add to it? Yes. I need to add everything that's on the outside, right? So 3s2 and then 3p1. That's the noble gas configuration. Yes. Them answers are preloaded. I'm like, wait a minute. Did I get hacked? No, that's totally fine. And everybody will not be on that level. Sometimes it's just you're having a good day. 8 a.m. is a strong time to start. So your brain may not be fully functioning at 9:18 in the morning. I get that. I had 4 hours of sleep last night. Remember, I got kids and a baby. One of them is a baby. So all engines are not firing. It's okay. We still here. We still in there. We doing it. So if you're hanging on and you're like, okay, I get it. I'm just a little bit slower on the uptake. That's fine. I have another example that I would like for you guys to try. Are y'all ready to do your own example, or do we need to walk through one together? Then let's do this one. And by let's, I mean you. I'm going to drink some tea. You can write the configuration for arsenic. I'm going to write both the full configuration and the noble gas configuration. If you just want to write the noble gas, that's fine. But just for clarity and making sure that, somebody else might be watching the video who doesn't get it, I want to make sure that I go through both ways and show how they're connected. So I'll give you 2 minutes to write the noble gas configuration for arsenic, or both configurations, and then I will jump in and do the same. Here we go. I'm going to start with the full configuration for arsenic. We've got 33 electrons to place for arsenic. Always start with the 1s. We fill that. We move on to the 2s and fill that. That's 4 electrons so far. We fill the 2p. That gives us 10 electrons. Fill the 3s. That gives us 12. 3p. We add another 6 to that. Now we're in 4s. We fill that with 2. We've got 20. Then we fill the 3d. We haven't done one of those yet today. So remember that the 3d comes after 4s. And that's 10 electrons. After that, you go back to the p's in n equals 4. And that's where arsenic lives, so we count 1, 2, 3. That's the full configuration. Took a little bit of time to write. Now we'll do the noble gas configuration. Let's figure out that noble gas core. Oh, bless your heart, you wrote it in the chat. You're fine. I didn't ask you to because that's a lot. But you got it right. So good. Anybody want to share what they got for the noble gas configuration? That's the one I was going to ask for because that's a lot easier to type. That's totally fine. That's totally fine. Yeah, so our core is going to be argon. Arsenic is in n equals 4. So we have to look at the noble gas in n equals 3 for that noble gas core. So everything in red brackets, that's argon. Then we add on to it what's between argon and arsenic. And that would be the 4s2, 3d10, 4p3. So those of you who are participating, y'all are on it. You're on point. If you are not putting your answers in the chat, just make sure that you get it. Because I'm here for everybody. Not just the folks that are typing in the chat. If you don't feel comfortable, you can always send me a private message send me something on course messages, catch me right after class, those kinds of things. So it looks like we're doing pretty well. Let's keep it pushing. We'll talk a little bit about valence electrons, and then we'll take a short break. This slide has a lot of text on it. I'm going to highlight the things you need to know. Valence electrons. They're the ones in the outermost principal energy level. They're the ones involved in chemistry. If you're trying to figure out which electrons are the valence electrons when you're looking at a configuration, they're the s and p electrons beyond the noble gas core. So in the one that we just wrote, where we had argon, and then we had 4s2, 3d10, 4p3, the valence electrons would be here and here. 3d10, n equals 3, that's not the outermost. It's slightly higher in energy than 4s, but they're not the outermost electrons. One way to figure out how many valence electrons you have for the representative elements is to look at the group number. And the group number you want to look at is the one that has the A behind it. So if you're looking at, say, oxygen, find oxygen on the periodic table and tell me what group it's in. Remember that the groups are the vertical columns. Yes. So oxygen is in group 6A. That means oxygen and everything else in that group has 6 valence electrons. Does that make sense to everybody? We're going to go over one more concept about valence electrons, and then we'll take a little bit of a break before we start talking about ions. Electron dot formulas. They're also known as Lewis dot structures. And this is just a way of representing the valence electrons of an element in a really easy to read visual format. The way you draw it is you have the symbol for the element in the middle. That's that SY here. And that represents the core electrons. Then you've got the dots on the outside all along the 4 edges. Those are the valence electrons. However many valence electrons you have, that's how many you fill in. If you have somewhere between 1 and up to 4 valence electrons, then you're going to have 1 dot per side. You never want to have electrons doubled up if there are available slots. So if you wrote, let's say you had only 2 valence electrons and you did this, that would be wrong. You need to spread them out. The example I always give is if you have family coming into town, you got cousins right around the same age. Anybody booking no hotel? Not in my family. Everybody's staying in the same doggone house, and you just gonna make it work. Guest bedroom? No. Adults get to sleep on the couch. If there's an air mattress, bless God, they get to sleep on that. The kids, y'all share. Twin size mattress, don't matter. So if you have 5 up to 8 valence electrons, you're going to share, just like that twin size bed. Head to feet. That's how it is. You fill them in. That's how you draw an electron dot formula. Let's do some real examples. Draw an electron dot formula for fluorine, which is a group 7A element. If it's in 7A, how many valence electrons does fluorine have? It's got 7. The symbol for fluorine is simply an F. So you go around, you fill in each spot. That's only 4. You go around again. Now you've got 7. As long as you've got 3 pairs and 1 unpaired, you can draw fluorine however you'd like. So that would be correct. And that would be correct as well. I'll give you a minute. I want you to try the second one. Draw an electron dot formula for aluminum. You obviously can't put this one in the chat, but just draw it in your notes or kind of have the image in your mind of what it'll look like. And I'll give you about 30 seconds. So I am definitely sipping tea in between. Shout out to Mr. Hefner for making me some tea because he knew my throat was sad. It is strong. He put like half a bag of cough drops in there. So I'm like, woo, wake up juice. That is what that is. So if I'm like, wow, that's why. Them cough drops, boy, they will wake your whole spirit up. Back to aluminum. Symbol for aluminum is Al. Oh, wow. Look at that. Ingenuity. It is somewhat possible. I'll take it. We've got 3 valence electrons. 1, 2, 3. They all get their own bed. No sharing. Could also do it like that, or any other arrangement where there's one side open. I think electron dot formulas are pretty easy, so unless there are questions, I'm going to say that we take a 5-minute break here. So it's about to be 9:38. Let's break until, we'll say 9:45. Then we'll come back and start talking about ions. So see you in about 7 minutes. All right, everybody, it is 9:45. We are going to get back to it and finish things up talking about ionization energy, which leads us to talking about ions. Ionization energy is going to be the third trend for the periodic trends. It's defined as the amount of energy required to remove an electron in the gaseous state. And in general, ionization energy increases as you go from the bottom to the top of a group and left to right across a period. What that means is that it gets harder and harder to remove that electron when you go from the bottom to the top of a group and from the left to the right on a period. This is the trend. Questions about ionization energy and what the trend is? I talk about why in the pre-recorded video. I'm not going to go into detail here for that. That's kind of one of those for your understanding, but not 100% necessary. So if we're ready to move on from ionization energy, let me know. Hopefully we're all back for break. I hope we're back, because I'm starting. So that was ionization energy. Ionic charges is definitely something you want to pay attention for. This information is going to carry over into Chapter 6. So if you don't understand ionic charges, Chapter 6 will be a struggle. I hope you're with me. We're first going to talk about positive ions. Most of the periodic table is comprised of metals. Metals react, in terms of chemistry, by losing their valence electrons to form positive ions. Let's say that we had a sodium atom. This is the electron configuration for a sodium atom. If I were to draw that atom, within that circle, I'm going to put a nucleus, and I'm going to use blue for protons, and there's 11 protons. We've also got some neutrons. We'll put 11 in there. There could be a few more. And we've also got electrons outside of the nucleus. 1s. There's our n equals 2. And then all the way out here by its lonesome is that 3s1. This is my sodium atom. Let me know if you're still with me. Even something simple like, I'm here. Thank you. Because I know this part is kind of abstract, and it's one of those places where students are just quiet and they're like, okay, class is going to be over at when? 10:30? Okay. I could watch a couple of episodes of this. So stick with me, y'all. We've got a sodium atom, and we talked about valence electrons being the outermost electrons. How many valence electrons does sodium have? You can find it on the periodic table and look at the group number. Tell me how many valence electrons it has. Yes, it's got one valence electron. And that valence electron is going to be the outermost principal energy level. So we're looking at the 3s1. This is our valence electron. When sodium is going to participate in chemistry, it's going to form an ion. It's going to lose that valence electron. I'm going to redraw redrawing here so you can see the difference. Still going to have my protons in blue. And my protons in green. Or excuse me, and my neutrons in green. This is a sodium ion. We've got 11 electrons in our atom. How many electrons do you see in the ion? You can literally count. You can either count them up here, because this is the electron configuration for the ion, or you can count the red circles in my crude drawing of an atom. There's 10 here. So in the ion, we've got 11 protons, 11 neutrons, and 10 electrons. An atom that's neutral has the same number of electrons as it does protons. So if we're starting out with a positive 11 from the protons, and we've got negative 11 from the electrons, then we've got no charge. That is neutral. What do you see with the sodium ion? If we do that same thing where we add up the proton charge and the electron charge, what's the charge on the sodium ion? There's an extra proton now. We've got positive 11. We've only got 10 electrons. So now we've got a positive 1 charge. That's what happens when you form an ion. You lose that valence electron. You now have more protons than you do electrons. So for positive ions, you have more protons than electrons. Is everybody with me so far? In general, for metals, and we're talking about the representative elements, your ionic charge is also going to be equal to the group number. We're talking about the one with the A behind it. Sodium is in group 1A. So 1A elements, they all have one valence electron, and they all form ions with a positive 1 charge. If you had group 2A, same thing. You would have 2 valence electrons, and they form ions with a 2+ charge. When we're talking about these forming ionic charges, we're really talking about groups 1A, 2A, and 3A. Carbon is a little weird. It doesn't really do ionic things. We'll talk more about carbon, sort of, in Chapter 6. So for now, just think of 1A, 2A, 3A. It tells you electrons, the valence electrons, and the charge of the ions formed. Now, we're going to go to figuring out the charge and writing the electron configuration for an ion. I'll fill in the group numbers here. And I'll walk you through an example. We need to write the charge and electron configuration for a magnesium ion. First, we'll handle the charge. Magnesium is in group 2A. That means it's going to have 2 valence electrons and a +2 charge. So the ion is Mg2+. Now let's do the electron configuration. We'll start with the magnesium atom. We'll write the noble gas configuration. Help me out. What's my noble gas core if I'm writing the noble gas configuration for a neutral atom of magnesium? It's going to be neon. Magnesium is in the N=3. We need to find the N=2 noble gas. Now we have to write everything that comes after that. So what do I write next to complete my configuration? Feels like it's just you and me in here. But yes, you're getting them answers right. That completes the noble gas configuration. But that's just the atom. When we lose 2 valence electrons, what we're doing is we're getting rid of the 3s2 electrons, because those are the valence electrons. They're the outermost electrons in the outermost principal energy level. So our new configuration is just going to be that neon core. Because if we're starting with magnesium that has 12 electrons, we're losing 2 electrons. Well, that means that we've got 10 electrons now. And the element on the periodic table that has 10 electrons is neon. Let me know if you follow that. We're going to do another example too. Let me know if you're still with me. Okay. We're going to add on another piece of vocabulary. Isoelectronic. Iso meaning same. Electronic, we're talking about electrons. So that means the same number of electrons. The magnesium 2+ ion and neon are isoelectronic. Neon has 10 electrons. Magnesium 2+ ion has 10 electrons. And they have the same configuration. Their electrons are arranged in the same way. On your homework, you'll definitely have to choose ions and atoms that have the same electron configuration. They're isoelectronic. That's all this means. Let's do another example. Let's do aluminum. We already did the electron configuration for aluminum earlier. So that I'm not going to have you redo. I'll just write that out. But what I do want to know, what's the charge? What is the charge for that aluminum ion? It's going to be 3 plus. It's in group 3A, so it's going to have a 3 plus charge. We did the noble gas configuration for aluminum. Since we're still in that N equals 3, we're going to use the N equals 2 noble gas, which is neon. And then we add on 3s2, 3p1. These electrons are my valence electrons. And we're going to lose those to form an ion. So if we're starting with 13 electrons, and we're losing 3 valence electrons, how many electrons will the aluminum ion have? Yeah, it's going to have 10. What do you think the aluminum 3 plus ion noble gas configuration is going to be? It's going to be just neon. When we write the configuration for the positive ions, we're losing all those valence electrons. And we're just left with that noble gas core. We've got to move on to negative ions. Negative ions, now we're talking about nonmetals. Fluorine, oxygen, sulfur. There aren't very many of them. they will gain electrons to form negative ions. If we have an atom, a fluorine atom, and it's got this configuration here, how many electrons are in that fluorine atom? All you have to do is add up the subscripts, y'all. Or the superscripts. Yeah. There's 9 electrons here. Now let's go over to the ion. How many electrons do you see in this configuration? You just add up the superscripts. These numbers up here. There's 10. We gained 1 electron. And that's how we form the ion. The ionic charge of a nonmetal representative element, you can figure it out like this. You take the group number and subtract 8. So fluorine is in group 7A. You'll take the 7, subtract 8, and that gives you -1. That's an easy way to figure it out. The charge tells you how many electrons your ion has gained. So this means that group 7A elements gain 1 electron to form an ion. What if you were in group 6A? Say that we had sulfur. What would be the charge of a sulfur ion? Six tells you how many valence electrons there are. For the charge, we have to do 6 minus 8 to get a -2 charge. So we're talking about negative ions now. A little bit more complicated, but not much. Let's walk through some examples. We'll deal with nitrogen right here. Nitrogen is in group 5A. It's also a nonmetal. Tell me what the charge of the nitrogen ion will be. Remember that you take the group number and subtract 8. Yes. So our charge is equal to 5 minus 8, which is equal to negative 3. Now we need to talk about this electron configuration. We're not going to do the noble gas configuration for this one. We're going to write out the full configuration. You always start with the 1s. We fill that. Then we drop down to n equals 2. We fill the 2s. We go across to the 2p. And we fill 1, 2, 3. That's for a total of 7 electrons. When a nonmetal becomes a negative ion, does it gain electrons or lose electrons? It's a negative ion with a negative charge. So if we think about our example, let's think about nitrogen. It currently has 7 electrons. The ion has a negative 3 charge. That means that it's got more electrons than protons. If that's the case, then we have to gain 3 electrons. So the charge here tells you how many electrons the atom will gain to become an ion. When we do that, we are filling the 2p. So we're adding 1, 2, 3 electrons. We now have 10 electrons total. We started with 7. Nitrogen is a nonmetal, so it gains electrons. We figured out that its charge will be negative 3 by taking the group number 5 and subtracting 8. That gives us negative 3. When it gains 3 electrons, it goes from having 7 electrons to 10 electrons. So it skips 1, 2, 3 spaces on the periodic table in terms of the electron configuration. So it now has the electron configuration of neon. Let me know how that feels. Then let's do an example. Now we're looking at bromine. It's in group 7A. What's going to be the charge of the bromine ion? You take that group number, subtract 8, that gives you -1. When your charge is negative, that means you're gaining some electrons. We'll write the full configuration for bromine. Start with 1s. We fill both. 1s2. N equals 2. We're going to fill the 2s. Then we're going to fill the 2p. Still not at bromine, so we have to keep going. We go down to N equals 3. We fill the 3s. We fill the 3p. Still not at bromine. We keep going. N equals 4. Fill the 4s2. In energy, the 3d10 comes next, and we're filling. It's 10 because we're filling all of them. We get to 4p. That's where bromine lives. 1, 2, 3, 4, 5. That's the full configuration. In that configuration, the bromine atom has 35 electrons. It is going to gain 1 electron to form the ion. So how many electrons will the bromine ion have? It will have 36 electrons. What other element has 36 electrons? Yes, krypton. So if we were going to write the noble gas configuration, that's what it would be. If we were to write out all of the, the whole full configuration, it would be the same thing as the configuration for krypton. That's negative ions. Questions here? So we were already doing the isoelectronic series kind of along with. So with this slide, this is just introducing that concept again, but we already talked about it. As practice, what you can do for yourself to make sure that you understand it is to write the configurations for these and convince yourself that they're all isoelectronic with argon. So you can go through the same process that I went through of writing the configuration with the atom, what the ion looks like, gaining or losing, and show yourself that they all have the same number of electrons and that the electron configuration looks like the configuration for argon. So now let's do reminders, because there's a lot of them. Mastering Chemistry, chapters 3 and 4, you've got an extension because Pearson was doing something. So you've got till the end of Wednesday. In the future, don't leave it till Sunday night. Try to work on it a little bit each day, or even a few days. But doing it all in one sitting is risky. You still have chapter 5, and that assignment is due March 7th, 11:59 p.m., just like usual. We've got exam 2, which covers chapters 3 and 4. That's going to be available tomorrow morning. It's multiple choice. Be about the same length as the first exam. Typically, students do a lot better on exam 2 than they do on exam 1. There will still be extra credit questions. So you can make up some ground if you didn't do as well on the first exam as you would have liked. Midterm grades. They are due on March 15th. I'm going to be submitting them. I always shoot for a day or two early. So we'll have a couple of exams, and we'll also have a lot of mastering chemistry assignments. So if you want to make sure that your grade is good, talk to me if you have mastering chemistry assignments to make up. If you miss some, I always allow students one chance of grace. I'll give you a time period where you can make up some of that homework and get some credit. That's the only time you get to do that. So if you struggled in the beginning of the semester, your money wasn't right, you joined the class late, what have you, talk to me, send me a course message, not an email. Send me a course message in Blackboard, and I will work with you. But if we get past midterms and you still haven't taken me up on that offer to try to make up stuff from the beginning of the semester, that offer is going to be gone. Y'all know who you are. Talk to me. Don't be ashamed. Things happen. Office hours are today. It's from 11:30 to 1. So stop on by if you can. If you can't, you can make an appointment with me. But I'm available. Please reach out. And use course messages. A lot of you sent me emails about mastering. I check course messages, and I may not get to it right away, but I will always get to you within a couple of days. The weekend is always a little bit iffy because, family and stuff. But I will never leave you stranded. So if you're like, man, I got a problem, Pearson ain't working, don't fear that you're going to lose points or something like that because you didn't get it done. If the website ain't cooperating, I'm not going to be like, oh, well, everybody gets a 0. That's completely unfair. If you have any questions beyond that, you can ask them now. Otherwise, you're free to go.